Now we come to module 4 of chapter 3. So far we have applied the method of successive approximations to obtain the Neumann series solution of Fredholm integral equation of second kind with continuous kernel and forcing function. Now we shall study the Neumann series solution to obtain the iterated kernels for the Fredholm integral equation of second kind with continuous kernel and forcing function. Now we consider Fredholm integral equation of second kind given by equation 3.37, which can be equivalently written in the operator form as I minus lambda capital K operating over phi, that gives fx. Here it has been mentioned before that capital I is the identity operator and K is the integral operator, which is given by integral a to b kxt phi t dt. And we have solved this Fredholm integral equation by the method of successive approximations. The successive approximations to the solution phi x of the integral equation 3.37 are represented by the sequence phi I x, I varies from 0, 1, 2, etc., where the 0th approximation phi naught x is given by fx and phi I x is equal to fx plus lambda into integral a to b kxt phi I minus 1 t dt for I greater than equal to 1. It has also been proved that the sequence phi ix tends to the solution phi x of the equation 3.37 as I tends to infinity, where phi x is represented in form of a series known as Neumann series, which is given by phi x equal to summation n equal to 0 to infinity lambda to the power n phi superscript n x as given by equation 3.39. Here phi superscript n x is given by the integral a to b kxt phi superscript n minus 1 t dt, n varies from 1 to etc., and phi superscript naught x is equal to fx as given by equation 3.40. Now note the last relation of equation 3.40, that is phi superscript naught x equal to fx. So the Neumann series given by the equation 3.39, that is phi x equal to summation n equal to 0 to infinity lambda to the power n phi superscript n x. In this series we separate out the term corresponding to n equal to 0, so that phi superscript naught x is fx, and if we separate out the term n equal to 0, then equation 3.39 can be written as phi x equal to fx plus summation n equal to 1 to infinity lambda to the power n phi superscript nx as given by equation 3.41. Now, this function phi superscript nx can be written in terms of phi superscript n minus 1x from the first relation of equation 3.40 as phi superscript nx equal to integral a to b k1 xt phi superscript n minus 1 t dt as given by 3.42, where k1 xt we write it as kxt. It is given by equation 3.43. Now, the function phi superscript n minus 1 t occurring in the right hand side of equation 3.42 can again be written in terms of phi superscript n minus 2 t by using the first relation of equation 3.40, so that the relation 3.42 can be written as phi superscript nx equal to integral a to b k1 xt dt is the outer integral and inner integral is integral a to b k t u1 phi n minus 2 u1 d u1. Now, here we interchange the order of integration to get phi superscript nx as double integral, where the outer integral is u1 integral, which is integral a to b phi superscript n minus 2 u1 d1, and the inner integral is the t integral, which is integral a to b k1 xt k t u1 dt. Now, we write the inner integral as the function k2 x u1, and which is given by k2 x u1 equal to integral a to b k1 xt into k t u1 dt, so that phi superscript nx can be written as integral a to b k2 x u1 phi superscript n minus 2 u1 d u1. In a similar manner, we can express phi superscript n minus 2 u1 d u1 in the right hand side of this expression in terms of phi superscript n minus 3 u2 as phi superscript nx equal to a to b k3 x u2 phi n minus 3 superscript u2 du2, where this k3 x u2 is equal to integral a to b k2 x u1 into k u1 u2 du1. If I continue this, that is, again we express phi n minus 3 superscript x in terms of phi n minus 4 and obtain the kernel in form of k4 xt and continue in this way, where a stage will come where phi superscript nx can be expressed as integral a to b kn xt into phi superscript naught t dt. Phi superscript naught t dt is ft, so that phi superscript nx is expressed as given by equation 3.44. Here kn xt is the integral from a to b kn minus 1 xs into kst ds for n greater than equal to 2 as given by equation 3.45, and k1 xt is our kernel kxt as given by equation 3.43. So now if I substitute phi superscript nx from equation 3.44 into equation 3.41, we obtain phi x as given by equation 3.46, and phi x is equal to fx plus summation n equal to 1 to infinity lambda to the power n integral a to b kn xt ft dt. Kn xt and k1 xt are defined by the equation 3.43 and 3.45 respectively. So, the Neumann series solution 3.41 or equation 3.46 can be expressed as phi x equal to fx plus lambda integral a to b capital R x t lambda into ft dt. Here the resolvent kernel capital R x t lambda is given by summation n to 0 to infinity lambda to the power n k n plus 1 x t as given by 3.48. This we have obtained by comparing equation 3.47 with equation 3.46. Now, we have obtained the solution phi x in the form 3.46 or 3.47 under the restriction that lambda satisfies mod lambda into m into b minus a should be less than 1 as given by 3.49, where capital M is the supremum of mod kxt, x and t ranges in the interval a to b. The kernels kn xt as obtained in equation 3.45 are known as the iterated kernel. We now observe that under the condition 3.49, that is the condition on lambda which is given by mod lambda into m into b minus a should be less than 1, the Fredholm integral equation 3.37 will possess unique solution as given by either of the forms 3.46 or 3.47, and this implies that the operator I minus lambda k associated with the integral equation 3.37 must possess an unique inverse under the condition 3.49, and we obtain phi x as I minus lambda capital K inverse operating on fx, that is equal to fx plus summation n equal to 1 to infinity lambda to the power n capital K n f operating on fx as given by equation 3.50, where using the equations 3.46 and 45 we see that the term capital Kn operating on fx occurring in the right hand side of 3.50, that is equal to integral a to p kn xt ft dt. The representation 3.50, that is phi x equal to fx plus summation n equal to 1 to infinity lambda to the power n capital Kn operating on fx. This shows that we have the following expansion formula involving the operator k as given by I minus lambda capital K inverse equal to I plus summation n equal to 1 to infinity lambda to the power n capital K to the Kn as given by equation 3.52, provided the sufficient condition on lambda, that is 3.49, is satisfied. So we have studied the Neumann series solution of Fredholm integral equation of second kind with continuous kernel and forcing function to obtain the iterated kernel, and we have written the solution of Fredholm integral equation in terms of the iterated kernel. We shall now illustrate this idea by considering few examples. Now we consider example 1. Find the iterated kernels and solve the integral equation phi x equal to 1 plus lambda into integral 0 to 1 xt phi t dt as given by equation 3.53. Here the kernel kxt is given by kxt equal to k1 xt equal to x into t, and the forcing function fx is equal to 1. The next iterated kernel k2 xt is equal to 0 to 1 k1 xs into kst ds. Substituting the values of k1 xs and kst in the integral, we obtain the value of k2 xt after simplification as x into t divided by 3. Similarly, k3 xt, the next iterated kernel, is the integral 0 to 1 k2 xs into kst ds. Here also we substitute the value of k2 and k and obtain after simplification the value of k3 xt as x into t by 3 square. Similarly, the next iterated kernel k4xt, which is equal to integral 0 to 1 k3xs into kst ds, it can be simplified to x into t divided by 3 cube. If we continue in this way, then the kernel, that is iterated kernel kn plus 1 xt, is equal to x into t divided by 3 to the power n. N ranges from 0, 1 to etc. Hence, the resolvent kernel in this case is given by capital R x t lambda equal to summation n equal to 0 to infinity lambda to the power n k n plus 1 x t. If I substitute the value of k n plus 1 x t from here, we obtain R x t lambda equal to x into t summation over n equal to 0 to infinity lambda by 3 whole to the power n. Now, this summation will converge to the value 1 by 1 minus lambda by 3, provided lambda satisfies the condition mod lambda less than 3. So, if this condition is satisfied, then R x t lambda, that is the resolvent kernel, is obtained as 3 x t by 3 minus lambda as given by 3.54. Hence, the solution of the integral equation 3.53 is given by phi x equal to 1 plus lambda integral 0 to 1 capital R x t lambda dt. Substituting the value of capital R x t lambda, we can write the solution of the given integral equation after simplification as phi x equal to 1 plus 3 lambda x divided by 2 into 3 minus lambda. Next, we consider example 2. Find the iterated kernel and solve the following integral equation. Phi x equal to fx plus lambda integral 0 to 1 e to the power x minus t phi t dt. Here kxt, the kernel, is equal to x minus t, and that is equal to first iterated kernel k1 xt. The next iterated kernel k2 xt is given by integral 0 to 1 k1 xs kst ds, that is equal to 0 to 1 e to the power x minus s into e to the power s minus t ds, which gives as e to the power x minus t. Similarly, the third iterated kernel k3 xt is given by integral 0 to 1 k2 xs kst ds, which can be simplified to e to the power x minus t. So, if I continue, then we obtain knxt as e to the power x minus t for all n. So that the resolvent kernel capital R x t lambda is equal to summation n equal to 0 to infinity lambda to the power n k n plus 1 x t equal to e to the power x minus t summation n equal to 0 to infinity lambda to the power n, and this summation converges to 1 by 1 minus lambda, provided mod lambda is less than 1, so that the resolvent kernel capital R is given by e to the power x minus t divided by 1 minus lambda. Hence, the solution of given integral equation is phi x equal to fx plus lambda by 1 minus lambda e to the power x into integral 0 to 1 e to the power minus t ft dt. Next, we consider example 3. Find the iterated kernels and hence solve f phi x equal to fx plus lambda integral 0 to 1 x into e to the power t phi t dt. Here the kernel function kxt is equal to x into e to the power t, and which is the first iterated kernel k1xt. The second iterated kernel k2xt is equal to 0 to 1 k1xs kst ds, which is equal to integral 0 to 1 x into e to the power s into s into e to the power t ds, which after simplification gives x into e to the power t. Similarly, k3xt, the third iterated kernel, is given by integral 0 to 1 k2 xs into kst ds, which after substituting the values can be simplified as x into e to the power t. Continuing in the same way, we observe that the nth iterated kernel knxt comes to x into e to the power t for n equal to 1, 2, etc. So that the resolvent kernel capital Rx t lambda is equal to n equal to 0 to infinity lambda to the power n k n plus 1 x t. Substituting the value of k n plus 1 x t, we obtain the resolvent kernel as x into e to the power t divided by 1 minus lambda. Here also the summation will converge for mod lambda less than 1, so that the solution of the given integral equation is phi x equal to fx plus lambda into x divided by 1 minus lambda integral 0 to 1 e to the power t ft dt, and this solution is valid for mod lambda equal to 1. In this module, we have studied the Neumann series solution of Fredholm integral equation of second kind with continuous kernel and forcing function, and represented this solution in terms of iterated kernels.